Hi everyone, today I will talk about estimating smooth GLM in non-interactive LDP model with public but unlabeled data. And this work is done with Huanyu, Zhang, Marco Gaboardi, and Jinhui Xu. So first, let me introduce our problem. So we study the generalized linear model. That is, we assume that there are n users, and each user has one data record. And we assume that each pair of xi and yi is i.i.d sampled from some distribution. So because we study the generalized linear model, so we assume that its probability density function could be written as the following. So here, phi is some cumulative generating function, or we call it as the loss function or the link function. And the psi is a function of the feature vector x. So in the linear model, we will assume that this psi is modeled by some linear relations. That is, it could be written as the inner product between the w star and x. And here, w star is some unknown vector. So in the non-product case, our goal is to get this w star. But how do we get it? Actually, we can get it through maximize the likelihood. And finally, we can get the following optimization problem. But in the private case, because we cannot get this w star, so our goal is to find some private estimator to make it to be close to this w star. And because we know that there are many price models, and in this paper, we will mainly focus on the non-interactive LDP model. But what is non-interactive LDP model? We know that in the local differential price model, the main difference, compared with the central DP model is that now our curator is interested. So that is, each user will get his or her own data record, and thus this is in the distributed setting. But because the curator is interested, so we cannot send our data directly to the server. We must go through by some channels or some algorithms. And in the local DP model, we need to ensure these channels to satisfy the DP property. That is, for each pair of x and x prime, we have the following inequality. And in the non-interactive LDP model, we assume that each user can only send a message once, and all the users, they must send simultaneously. So the procedure of the protocol should be, first the server sends messages to all the users, and then all the users, they give feedback simultaneously. And actually, there are many basic properties of LDP algorithms, but I will skip them here. So actually, there are many previous results study the empirical risk minimization in the non-interactive LDP model. So Smith first studied the topic, and they showed that there is an epsilon LDP algorithm whose sample complexity to achieve the alpha is this one. So we can see that in this sample complexity, there are two terms that are exponentially dependent on the dimension LDP. And they also showed that in general, these two exponential dependencies are unavoidable. However, we can also show that for some specific loss functions, for example, for the linear regression, the sample complexity actually can be reduced to only polynomial size. And motivated by this, there are many papers study on some specific class loss functions in the LDP model. For example, Zhang studied the GLM in LDP model, and they show that when the loss function is smooth enough, then the sample complexity could be reduced to quasi-polynomial in 1 over alpha and linear P. And recently, we extend their result to the general convex GLM loss and showed a sample complexity that is exponential in 1 over alpha and linear in P. So here is a summary of the previous results. We can see that all of these results, their sample complexities are not polynomial, but except for the first one, but it is only for the linear regression. Thus, to our best knowledge, there's no previous result with polynomial sample complexity. And due to these negative results, there is also no study on the practical performance of these algorithms. However, on the other side, we know that there are many papers, study about the central DP model with public but unlabeled data, and they show that when the query has some public but unlabeled data, then it is possible to reduce the sample complexity. If these public data have the same marginal distribution as the private ones. But we don't know whether it is true for the LDP model, because none of this work can be extended to the NLDP model. So our question is, can we further reduce the sample complexity of GLM in NLDP model if the server has public but unlabeled data? So next, I will talk about our contributions. So we study about the GLM in LDP model with public but unlabeled data. That is, we assume that the size of the public unlabeled data is n, and also we assume that each sample has the same marginal distribution as xi. So first, we study the case when the feature vector is some Gaussian distribution, and we show that there is an algorithm, whose sample complexity for public and the private data, to achieve the alpha error, in the L2 norm is this one and this one respectively. We can see that all of these two terms are polynomial size. And our second contribution is we extend from the Gaussian distribution to the sub-Gaussian distribution with bounded L1 norm. And we show that there is an epsilon delta LDP algorithm whose sample complexity of the private and the public data, to achieve the error alpha in L infinite norm, are this one and this one. But here we note that here we need to assume that our error alpha cannot be small enough. That is, we need to assume that alpha is greater than 1 over square root of p. And finally, because all of our results are polynomial size, so we also provide some experimental study of our algorithms on both synthetic and real-world data. So this is a summary compared with the previous result. So due to the time limit, I will just give a brief introduction of our method. So first, we consider the Gaussian case, and our motivation is the Stein's lemma. The Stein's lemma shows that if x is some Gaussian distribution, then the W star of this problem can be written as a constant C phi times the WRS. And here C phi is a constant, but how do we get it? It is just the fixed point of this function. And the WRS, you can see it is just the ordinary least square vector. So that is, if we want to get this W star, it is sufficient to estimate WRS and the underlying constant C phi. Let's see how do we estimate these two terms in our model. So we can see that W star is just the linear regression vector, right? So we can easily estimate it, in the NLDP model. That is, we let each player perturb his or her sufficient statistics, by adding some Gaussian noise, and then the curator receives these perturbed sufficient statistics, and then it can estimate the WRS, right? And when we get this estimator of the WRS, we can use it, and get the fixed point of the empirical version of this function, and then we can estimate this C phi. So this is our algorithm. It's very simple. That is, first each user will perturb their sufficient statistics, and then they send to the curator, and then the curator will get a private version of the linear regression estimator. And combining with the public unlabeled data, it can get a constant C. And finally, it will output C times the private linear regression estimator. So this is our algorithm, and this is our theoretical result. But due to the time limit, I will skip it here. And our second contribution is extension to the sub-Gaussian case. For the sub-Gaussian case, it's almost same, but there are still some difference. The first one is that, although we can see that, W star is still quite close to C phi times WRS, but it is not a equality, it's an inequality. That is, there is a biased term, okay? That is 1 over square root of p, okay? And the second difference is that our error, okay, of this bias term is in the L infinity norm. And the third difference is that it is the formula of the C phi. In the previous Stein's lemma, we can see that C phi is just something related to xi and WLS, right? But here, C phi is something related to W star, not WLS. So that's three differences, okay? However, because we can see that W star is still very close to C phi times WLS, so here we can use almost the same method as in the previous case. Okay, that is, we first get the private version of WLS, and then we can solve some equation to get an estimator of C phi to estimate the W star, right? And this is our final algorithm, and this is our result. So we can see there are two errors. The first one is caused by the estimation error, okay, of the C phi, and the second one is caused by the estimation error of our linear regression estimator, and the third one is the bias term, okay, caused by our previous lemma. Okay. So finally, we conduct some experimental results. The first one is conduct on the synthetic data, and we can see that when epsilon is large, or when the dimensionality is small enough, then our private estimator, okay, is very close to 0. Okay. And then we conduct some results on the real data. And we can see that when the epsilon is large enough, then the accuracy will be close to the non-part case. Okay, and for example, the left line is for the cover type, and the red one is for the SUSY data. And this result shows the effectiveness of our algorithms. So that's all for my talk. Thank you very much.